if you remember when we were talking about how we're thinking about topics, especially in the lead up to next assessment, we covered motion before, so displacement, velocity, acceleration, the basics of it. Then we spent that really brief time on exponential growth and decay, right? So I hope that after we got all of the weird terminology about growth rates and that kind of thing out of the way, it was quite simple. Like it's just, you differentiate and then you stick stuff in or you integrate. It's not that much different from what you've already been doing. Now we're coming back to motion. So this is the 3-unit part of motion. Hopefully today you'll gain an appreciation for why this is 3-unit motion. That there actually is, it's not just like the same stuff and more of it. You actually have to make some conceptual leaps and some thinking which is a little more rigorous and difficult than what we had to do on a 2-unit, which is kind of just, okay, differentiate, here's some cool equations, and then you just put numbers into it. This requires a bit more thought. Okay, so let's revise. We started with our equations of motion, right? And we call displacement x. So we'd say, usually, x is some function of time, right? And then because we're thinking calculus, right, we think about how displacement changes. So we call that x dot, right? But the normal word we use for it is velocity, right? So we'd say v is equal to how your displacement is changing, right? So that's dx on dt. You know, distance over time, kilometers per hour, meters per second, that kind of thing, right? Should make my dot a bit clearer. Sorry. And then we went one more further step. We said you differentiate again, okay? What you're going to get is how velocity is changing, right? Which you could think of in two ways. You can think of that as acceleration, right? Or if you're more physicsy, you can think of it as a force. It's the same idea, right? Something that's acting upon something else and making its velocity change. And we said, well, look, you want to take your velocity and see how that is changing over time. And since velocity itself is also a derivative, getting acceleration, or the force, is just taking the second derivative. Right? Okay, now that's all revision. Now the important thing you want to get is that all of these, what they have in common, is that they're all functions of time. They're all telling us characteristics about the motion of an object in terms of when, right? Do you know, have you got some equations that govern where something is at a particular time, and then you can sort out the rest of it, okay? But you remember, this topic is actually not called 3-unit motion. Does anyone remember what its real name is? It's a bit long and awkward. It's called, this is probably worth writing down since we're sort of, we're starting this, right? 2-unit motion is displacement, velocity, and acceleration, which is what we just looked at, okay? But 3-unit motion is, I think it's applications of calculus to the physical world. Okay, so that's why there's so much like, oh, this feels like physics, you know, forces and that kind of thing. Now, here's the reason why I'm drawing attention to the name and why it's actually a really good name, even if it's a bit of a mouthful. In reality, we usually, well, a lot of the time, we don't know things about motion, characteristics of motion, in terms of time. Okay, far more frequently, we know them in terms of displacement. Okay, so instead of knowing things about an object and how it's moving based on when it is, what time it is, we know them based on where it is. Okay, so examples, you know, you got two objects, okay, with different masses. Okay, we say that these two objects attract each other everywhere, all the time, right? But how much is their attraction governed by their motion toward each other, right? This sort of force here, which we call gravity, right? It's not so much about time. How do we usually express it? Does anyone know the equation for gravitational attraction? No? I think it's something like, you've got to take the product of the masses, right? So the more massive your objects are, the more they're going to attract each other. And then you divide by, does anyone remember? Anyone? Yeah, the square of the radius, right? In terms of like what that distance is, right? So the further things are apart, the more this denominator is getting bigger. Okay, so the further things are apart, the less things are acting upon each other, and the heavier they are, the more they're acting upon each other, right? So you can see here, right? Gravity obviously makes things move, makes things orbit, and so on. But it has nothing to do with time, at least not in the way that we usually think about it. It's more about how close you are to something or how far you are. And most forces are like that. Like magnetism, all the different forces of nature, they're sort of, that's the way they work. So, how can we express any of these? Well, obviously, displacement is not really, there's not much use expressing displacement in terms of displacement, so we'll leave that one behind. But how can we get velocity and acceleration in terms of displacement? So instead of dt's here, instead of differentiating with respect to t, we want things on dx, right? Okay, we want to see if we can express velocity and acceleration as functions of displacement, differential equations. Okay.